Hello everyone, welcome back. Let us continue our discussion on reinforced concrete design. We are in week 10 and this is our first lecture. In this week, we are going to learn design of circular tank. Now, if you recall, in the previous week, we designed underground tanks. This time, we are going to design storage tanks, which are actually above ground. Now, these tanks are actually of different shapes, but out of that, circular tanks are most preferred because it is convenient and economical. And for the same storage volume, if you go for rectangular tank, we need more materials compared to circular tank. And that's the reason circular tank is preferred. Not only that, the geometry of the circular tank is also beneficial because it has no corners, no sharp corners, and therefore it is easier to ensure watertightness, right? And as you can see here, these type of tanks, they have a base and then above ground, this is the storage tank. So also sometimes there are cover. So if it is there, we need to design the cover also. But the fact is, first the ground is prepared and then the base is prepared and then the side walls are constructed. Now for that, let us first quickly go through the permissible stresses. Now for liquid storage tank, recall we use this code, and the table 1 of this code which we used in our previous week, it says that the grade of concrete should be M30. So at least we should use this grade for the design of storage tank, right? Now, when we design these type of tanks, we have to ensure that at this region there is no leakage. Not only that, for any storage device, it will be under water pressure, and under that water pressure, this wall is going to bend like this, or if there is a roof here which is holding it, then the wall behaves like a propped cantilever. In any case, it will develop tension in concrete. And cracking near the water surface is not at all recommended for liquid storage tank, because the moment concrete starts cracking, water will seep in and it will start corroding the rebars. So in our entire design, we will ensure that there is no cracking. And at the same time, the junction between the side walls and the base, we have to make it leak proof. So accordingly, we have to design the cross section so that it can withstand tensile and shear stresses. And for that, we have to have a minimum grade of M30. Now, for all practical design, we normally use concrete that does not carry tensile stress, because as you all know, concrete is weak in tension. So as we progress, you will see concrete tensile force. If you recall also from our previous discussion, concrete tensile stress is very less. And that's the reason we have to provide sufficient amount of reinforcement. But depending upon the wall thickness, we can go for a single layer reinforcement or a double layer reinforcement. As we progress, we will see these details. The fact is, again, for this type of structures, these rebars, they are the most critical part, and we have to design them accordingly. And for steel, the permissible stresses are here. So when the reinforcement is placed on the surface directly exposed to liquid, the allowable stress is 115 Newton per millimeter square for mild steel and 130 Newton per millimeter square for HYSD bars. If the reinforcement is provided on the face away from the liquid in members less than 225 millimeter thick, the same permissible stress may apply. So, while designing the reinforcement, we have to keep in mind that for HYSD bar, it is 130 Newton per millimeter square. Okay. Now, for this type of tank, as you can see on your screen, we first need to prepare the floor slab. Now, if the tank is founded on good soil, the base slab must safely transfer the combined load. So, we'll have the liquid here. It has its self weight plus some additional loads may also come depending upon the geometry. Then there is, as you can see, it has a base below it, and that base must safely transfer the stress below the soil. Now, generally the slab thickness are in the range of 150 to 200 millimeter, and nominal reinforcement is provided as mesh on both top and bottom face. So, at the top and bottom, we provide required amount of reinforcement, but in any case you have to provide a nominal reinforcement there. So before casting the slab, the ground is first compacted, it is prepared. Then once the soil below this base slab is prepared, then lean concrete mix is normally laid of 75 millimeter thick, and it is made of M10 grade concrete. Then on top of this lean concrete, a tar or similar coating is applied before, putting the base slab on top of the prepared ground. Now, in some waterlogged areas, instead of M10, we normally use M15 concrete, which is a better one for this ground preparation. Now, let us look into the details of minimum reinforcement. So, for tank walls, floors and roof slab up to 100 millimeter thickness, the minimum reinforcement in each of the two particular directions must be 0.3% of the concrete cross-sectional area. Remember, the thickness up to 100 millimeter. If the thickness is between 100 millimeter to 450 millimeter, the minimum reinforcement is gradually reduced from 0.3% to 0.2%. So if the thickness is more, obviously the requirement of reinforcement is less. So we can reduce from 0.3 to 0.2%. So in any case, we have to provide this much of reinforcement. For floor slabs resting directly on ground, the minimum reinforcement should not be less than 0.3% of the gross cross-section area. And when the section thickness is 225 millimeter or more, reinforcement should be arranged in two layers, one layer near the face. If you recall, I already explained that if the thickness is more, we have to have two layers on each face to satisfy the minimum reinforcement requirements. If the thickness is small, we can have a single layer only. Okay. Now, the circular tanks, it can be designed in two different ways. As you can see, it has a base slab and it has side walls. Now, these side walls can be firmly connected at the base, or it may be not rigidly connected. So there are two options available when we design circular tanks. So tanks with flexible but watertight joints between wall and floor, and tanks with rigid connection between wall and floor. So these are the two options when we see the detailing, it will be further clear how these two different types of connections can be made at site. Now let us consider the first option where we have circular tank with flexible joint. Now for this type of tank, obviously it will experience hoop tension, and at the same time hydrostatic pressure increases from 0 at the top and gradually increasing to its maximum at the bottom. And the maximum hoop strength tension occurs at the base of the wall. Now let H be the, capital H be the height of the stored water, D, capital D is the tank diameter, W is the unit weight of water, capital T is the hoop tension, and sigma ST is the allowable stress. Now if we go at a depth H below the water surface, their hoop tension is given by this expression. So T is half times W times H times D. Obviously, if H is maximum, that is capital H, the hoop tension is also maximum. It is half omega times capital D times capital H. Now, because we already fix the allowable stress, we can find out still using this expression, because the area of steel multiplied by the allowable tensile stress must balance this hoop tension. So we can find out the amount of steel required for this design. Now, if the wall thickness is less than 225 millimeter, then the reinforcement may be placed at the center of the wall because thickness is less. For thicker walls, steel should be provided near both faces with at least 25 millimeter clear cover. So this is the minimum amount of clear cover we have to have for a storage tank. Now the hoop tension reduces from bottom to the top. So if this is the tank and this is the liquid, as we go near the water surface, recall the expression for hoop tension, it is half omega H times D. So this H, if it is reduced, obviously the hoop tension also reduces. So to cater that, what we can do, we can reduce the amount of steel as we go towards the water surface. Remember, that is the hoop tension steel that we can reduce. Now the minimum reinforcement should not be less than 0.3%. and spacing between the steel should not exceed 3 times the wall thickness. So spacing should not be more than 3 times the wall thickness. Its capital D is the diameter. So let me write D wall. Now how to find out this wall thickness? For that, let us assume that A is the concrete area, AS is the steel, M is the modular ratio, and T is the wall thickness. Then the equivalent composite area, if you recall, this is the expression. So here what we do, with the help of modular ratio, we convert the area of steel into equivalent area of concrete. And here is the expression. Now, wall thickness must be selected so that the tensile stress in the composite section does not exceed the permissible value. So, from this expression, we can find out the thickness of the wall. Now, for M30 concrete, sigma CT is 1.5 Newton per millimeter square, which is given in table 1 of this code. So, from this expression, the outcome is the thickness required. Now, there is a empirical expression. So thickness you can assume using this approximate formula, which is 30 times H plus 50, where T is the wall thickness in millimeter and H is the depth of water in meter. We will see how we can use this expression and find out T, and then once we find out T, then we have to check whether it satisfies this requirement of permissible tensile stress. Now, using this expression, what we get first, the idea of the thickness that we are going to provide for this circular tank. But in no case, it should be less than 150 millimeter. So, T minimum is 150 millimeter. Now, apart from hoop reinforcement, there will be vertical reinforcement. So, if this is the wall, so we have hoop reinforcement and there will be vertical reinforcement also. So, that reinforcement is provided as per the minimum reinforcement requirement provided in the codal provisions, right? So, with that background, let us take an example. Let us design tank. So, it will provide a storage of 4.5 lakh liters of water. The wall and floor are connected with a flexible joint, just note it. And you can see the diagram here, which shows that we have a base with the ends thickened, and here at this location the side walls are just placed in this groove. Of course, it has to be watertight, there should be no leakage, and it should satisfactorily transfer the loads also. But the fact is, in this flexible joint, it is indeed not monolithic. And the tank is resting on ground level. Concrete used is M30 and steel is Fe415. So, first let us convert the capacity in meter cube. So, we have 450 meter cube of water. That is the volume of the tank. Now, let us assume this depth, total depth is 3.75 meter. So, we can find out the plan area, which is 120 meter square. Now, we can easily find out the diameter of the tank, which is 12.36 meter. So, we can provide 12.4 meter diameter for this circular tank. Now, once we find out the diameter of the tank based on the capacity of water storage, then next thing is we can find out the maximum hoop tension. And as you can see here, maximum hoop tension is at the bottom, where we have half omega or W times capital H times capital D is the total hoop tension. Now, if you consider unit weight of water, 10 kilonewton per meter cube. So, this is omega or W. So, the hoop tension we get 232.5 kilonewton. Now, once we find out the hoop tension, we can find out the area of steel AS, which is capital T by sigma ST. And for the problem, we have sigma ST is 130. So, we get the area of steel required is 1789 millimeter square. So, what we do, we provide 16 millimeter diameter bars, and then the spacing, you can calculate, spacing will be 112.3. So, we adopt 110 millimeter center to center. That means we actually provide 1827 millimeter square of steel as opposed to 1789 millimeter square, which is required. So, that is okay. Then comes the wall thickness. For that, we have M30 concrete, and the modular ratio is 13, and the permissible tensile stress of concrete is 1.5 Newton per millimeter square. So, what we do, we first find out the equivalent composite section. So, recall this expression. So, this is the equivalent area, concrete area. So, T by equivalent concrete area is equal to sigma CT, which is 1.5. So, from this expression, we get T as 133 millimeter. Now, recall the empirical expression. From that, we get thickness of 162.5. Recall the minimum thickness. So from this expression, the thickness what we get is less than 150. So we have to provide a minimum thickness of 150, but the empirical expression gives us 162.5. So we provide a thickness of 170 millimeter. Now, this side wall, which is 170 millimeter, it is relatively thin, and therefore we can place the reinforcement at the center. Now, as the hydrostatic pressure reduces towards the top, the required hoop reinforcement also decreases upward, and hence we can actually curtail the reinforcement as we go towards the surface of the water. That we'll see in a minute. So let us first design the hoop reinforcement towards the top. So it is at 2.5 meter below the top. So hoop tension reduces, and the required area of steel we can calculate from the maximum area, and it is 1193. So we provide 16 fiber, the same bar, but this time with a spacing of 160 millimeter. Just check the spacing that you can calculate. So up to the first 2.5 meter we provide 160 millimeter. Then at the 1.25 meter below the top, we further reduce it, and the area of steel is 597 millimeter square. So 16 5 bars we provide at a distance of 330 center to center. Recall there is a requirement of maximum spacing, so our thickness is 170. So this spacing is okay. Now we also have to provide vertical reinforcement. For vertical reinforcement, the minimum is 0.3, but recall here, if the thickness is in between 100 millimeter to 450 millimeter, we can actually reduce the percentage for minimum reinforcement, and the reduction is gradually from 0.3 to 0.2%. So let us do that. For our case, we have 170 millimeter thick wall. So what we do, we reduce that gradually, and ultimately because of this thickness, we get the minimum percentage of steel is 0.28. So 0.28% of steel we have to provide as the vertical distribution reinforcement. So the area is 476 millimeter square. So let us provide 10 millimeter bar at the rate of 160 millimeter center to center. So that completes the design of the wall. We'll see the detailing. Now let us move over to base and its design. So let us provide a thickness of 160 millimeter base. As per minimum reinforcement for water retaining structure, it has to be 0.3% of the gross cross-sectional area. So the requirement is 480 millimeter square. Now this reinforcement is provided on each face of the slab, that is at top and bottom. So we have to provide either side. So since the minimum steel required is 480 millimeter square per meter width, reinforcement at the top face and bottom face are provided equally. So we distribute this as 240 millimeter square per face. So this can be designed with 8 5 bar, and for that spacing is 208 millimeter. So we adapt 8 5 bars at the rate 200 millimeter center to center on top and bottom faces of the slab. And we can provide a freeboard above the water level as 150 millimeter. So that completes the design. So let us go for the detailing. Now as you can see here, we started with a flexible connection between the wall and the base, and look at the detailing here. When we'll consider the rigid joint, we'll actually compare with this, and you'll see how the difference between these two type of connections are designed. Here the thickness is 170. So we have a single layer, and as you can see, the total height is divided into 3 regions. At the base we have maximum hoop tension. Accordingly, we provide 16 phi bar at the rate 110 center to center. As we go above, in the middle layer we have same 16 phi bar at the rate 160 center to center, and at the top we have 16 phi at the rate 330 center to center. So these regions are marked. There are 3 regions. At the base we have maximum amount of hoop reinforcement. Then there are some distribution reinforcement that we have already designed, which is 10 phi at the rate 160 center to center. And for the base, the net thickness is 160 millimeter. We have 8 phi at the rate 200 center to center both ways and in both faces. And as you can see, because this wall rests on the slab, so the edge of the slab is thickened and the side walls are placed above this thickened base slab. So that's how the design of the circular tanks are made. Now, with that, let us close here. In our next class, what we'll do, we will see how we can go to the design of rigid connections as opposed to flexible connections, what we have covered today. So go through these steps. If you have any doubt, do let us know. We will clear your doubt. So in the next class, we will see the design of circular tank with rigid base. Thank you very much.